Okay, so now we're going to talk about some of the situations in which you would use a heuristic, which we've kind of already talked before, but we're going to sort of review some of it. Um, so the reason why an exhaustive solution space is impossible or not feasible is because the search space is too large for some problems, and it's so large that finding a solution is not feasible due to its high computational complexity. And this is for humans as well as for computers. But in this scenario, I'm primarily going to talk about humans. For other problems, there is no correct solution, right? The problem is what we would call uncomputable. There is no perfect solution, which we're going to talk about in a second, what that means in a more precise way. For other problems, it's not clear what the goal state is or which operators or tools are available for getting the solution. So we would say that these kinds of problems are ill-defined, problems in which the goal state, even the initial state, and or the operators are ill-defined or not clear. And again, we'll talk about that later. But first, I'm going to talk about uncomputable problems. But first, what I want to, I just let, we're going to talk about uncomputable problems, but I just want to mention that in all of these cases, we must use some sort of collection of heuristics in order to get to the correct answer. And if there is no single unique answer, then it has to be a good enough answer at least. So we have to deal with a lot of uncomputable problems. Most, or not most, but many psychological problems are uncomputable. And so here are just a few of them that I'll talk about in more detail. So one is ambiguity resolution in natural language processing, learning natural language grammars as well. There's the problem of reference indeterminacy in learning new words, as well as inverse optics in vision. So in order to talk about what I mean by uncomputable, it's useful to go back to the algebra example that we discussed in a previous lecture. Uh, and then we'll talk about what each of these uncomputable problems are like and how we deal with these problems. So imagine if your problem is 3x equals 24, and you have to solve for x. So solving for x just means, you divide each side by 3, and so 24 divided by 3 equals 8, so x equals 8. In this example, we can solve for x because we know that there's only one unknown variable. And so we would say that this problem is well determined as the problem is constrained enough for us to solve for one or solve for x. However, this wouldn't be the case with the problem x times y equals 24. This is because there are a number of x's and y's uh, that when you multiply them together equal 24, right? It could be that x is 8 and y is 3, or y is 8 and x is 3. But it could also be that x is 4 and y is 6, or the reverse, right? X is 6 and y is 4. So in this case, we have two unknown variables, and as a result, we would say that this problem is underdetermined or not constrained enough to solve for x. And so, as I said, many psychological problems are underdetermined. Again, we've talked about this. So with color vision, what's the color of an object? Well, light 2 is that's what you as a perceiver gets reflected into your eye, but you want to know the color of the object, but you only have light 2, right? So in order to know the color of the object, you also have to know the color of light 1 because the color that light 2, the color of light 2, what you see is a product of both the object color and the light 2 color. And so if you don't know light 1, which we don't sometimes, we can't do it. We can't solve for the object's color. So in order to infer the object's color, we must have additional information or make some assumptions about light 1. And again, just showing it in another way, So we have light 2, that's a known thing, that's a known variable. We know what that color is, but we don't know the object color or light 1. And if we did know light 1, we would have enough information to determine what the color is. But because we don't, we must impose constraints on this problem. So yeah, our visual system must impose additional constraints onto this underdetermined problem. And when we impose constraints on the problem, we make assumptions based on our previous experiences or use heuristics or rules of thumb. In this case, we make an assumption about the other color, the light 1 color, which would presumably be based on previous experience or maybe even context. So in the next video, we'll talk about some of the computational problems that we face and some methods that we have for mitigating these problems or partially solving them in some sort of suboptimal way.